When we look up at our sun, we see a tyrant. It contains 99.8% of all the mass in our solar system. It creates a gravity well so deep that it holds planets, asteroids, and comets in check billions of kilometers away. It is a ball of plasma so vast that you could fit 1 million Earths inside it. To us, standing on our small rocky world, the sun is the definition of a massive. But in the grand catalogue of the cosmos, our sun is nothing more than a yellow dwarf. It is a grain of sand on a vast beach. We know of stars that make the sun look ridiculous. We have found red hypergiants like Stephenson 2-18, a star so bloated that if you placed it in the center of our solar system, its surface would extend past the orbit of Saturn, swallowing Jupiter whole. For a long time, astrophysicists thought they understood the upper limits of nature. We believed physics had a hard ceiling. It is called the Eddington limit. The theory states that if a star gets too massive, around 150 to 200 times the mass of the Sun, the outward pressure of its own radiation becomes so intense that it overpowers gravity. The star essentially blows itself apart before it can grow any larger. It shreds its own outer layers. But recently, the James Webb Space Telescope has peered into the dawn of time and found something that shouldn't exist. It has found the chemical fingerprints of celestial monsters that defy the Eddington limit. These are not stars that are 10 times, or even 100 times the mass of the Sun. We are talking about primordial giants that were 10,000 times more massive than our Sun. These are the celestial monsters. And they may solve the biggest missing link in the history of the universe. Before we travel back 13 billion years to hunt these giants and understand how they shaped the cosmos we live in today, if you love uncovering the secrets of the deep universe and the mysteries of astronomy, please take a moment to subscribe to the channel and hit the like button. It helps us immensely in our quest to map the cosmos. To understand why these monsters are so important, we first have to look at a mystery closer to home. We need to look at the oldest structures in our own galaxy. Globular clusters. Globular clusters are beautiful, dense spherical cities of stars that orbit the halo of the Milky Way. They are fossils. Some of them, like the magnificent Omega Centauri, are nearly as old as the universe itself. They contain millions of stars packed into a tiny space. For decades, astronomers believed these clusters were simple families. The standard model of star formation told us that all the stars in a cluster were born at the same time, from the same cloud of gas, and therefore should have the exact same chemical composition. But when technology advanced and we analyzed the light from individual stars within these clusters, we found something strange. We found a crime scene. These ancient stars are polluted. They contain impossibly high levels of nitrogen, sodium, and aluminum, but almost no oxygen. This unique chemical signature, known as the abundance anomaly, doesn't make sense. Normal stars, like our Sun, burn hydrogen into helium. They don't churn out this specific cocktail of elements in these massive quantities. The chemistry was telling us that something else had been there first. Something massive. The only way to create this much nitrogen is through extreme heat, temperatures far higher than the core of a normal star. We needed a bigger oven. For years, astrophysicists were stumped. What kind of cosmic engine could pollute millions of stars across a cluster with this specific chemical ash? Enter the James Webb Space Telescope and its ability to look back in time. By looking at the distinct light signatures from the very early universe, specifically a galaxy designated GN-Z11, which exists just 440 million years after the Big Bang, astronomers found a match. They found the theoretical proof of a beast that we have nicknamed the supermassive star. Imagine a star not just made of gas, but a sheer wall of superheated plasma. A star with a mass of 10,000 suns packed into a relatively small volume. If such a star existed today, it would be terrifying to behold. It wouldn't look like a calm yellow disk. It would be a blindingly blue-white inferno, pulsating violently. Its brightness would outshine entire galaxies. But the real action is happening inside. In the core of our Sun, the temperature is about 15 million degrees Celsius. That is hot enough to fuse hydrogen. But inside a supermassive star, the crushing weight of 10,000 solar masses drives the core temperature to a scorching 75 million degrees. At these extreme temperatures, nuclear fusion doesn't just happen, it goes into overdrive. The star ignites a process known as the hot CNO cycle, carbon-nitrogen-oxygen. It is a violent, runaway process that cooks hydrogen into helium with incredible speed and dumps massive amounts of nitrogen as waste. This explains the pollution in the globular clusters. These monsters lived in the crowded, dense nurseries of the early universe. As they burned with furious intensity, they were unstable. They shed their outer layers constantly, spraying the surrounding gas clouds with nitrogen-rich wind. The normal stars we see today in clusters like Omega Centauri were born from that polluted gas. They are the children of these monsters, carrying the chemical DNA of their giant parents. But how did they grow so big without blowing apart? How did they cheat the Eddington limit? The answer lies in the unique conditions of the early universe. Today, stars form from clouds that have heavy elements, metals, in them. These metals absorb radiation and push the gas away, stopping the star from growing. But in the dawn of time, the gas was pristine, almost pure hydrogen and helium. This allowed gas to fall onto the star faster than the radiation could push it away. It allowed the star to gorge itself, growing to impossible sizes before physics could intervene. But here is the most tragic part of the story. You cannot be this big and live a long life. The candle that burns twice as bright burns half as long. And these stars burned 1,000,000 times brighter. Our Sun will burn steadily for 10 billion years. These supermassive stars? They were cosmic flashes in the pan. They likely lived for only 2 million years. To the universe, that is less than a blink of an eye. They lived fast, burned bright, and died young. And their death brings us to the second great mystery they solve. One of the biggest problems in modern cosmology is the supermassive black hole problem. When we look at the very early universe, we see quasars, active black holes with masses millions or billions of times that of the Sun. We see them fully formed when the universe was only a toddler. This shouldn't be possible. A normal black hole, born from the collapse of a normal star, starts small, maybe 10 to 100 times the mass of the Sun. It then has to feed to grow. But black holes are messy eaters, they can only consume matter so fast. There simply wasn't enough time in the early universe for a small black hole to grow into a billion solar mass monster. Unless they didn't start small. The supermassive star theory offers a terrifying, elegant solution. When a star of 10,000 solar masses runs out of fuel, it doesn't just explode as a supernova. A supernova happens when the core collapses and bounces back. But here, the object is too heavy. Gravity wins instantly. The entire star collapses directly in on itself. It bypasses the explosion. It punches a hole straight through the fabric of spacetime. It creates a direct collapse black hole. This means the seed was not a small stellar remnant. The seed was already massive, tens of thousands of times heavier than the Sun, from the very moment of its birth. This gives the black hole a massive head start. It explains how the monsters at the centers of galaxies like M87 or our own Milky Way got so big, so quickly. So, when we look at the majestic spiral of the Milky Way, or the dark heart of the black hole Sagittarius A** at its center, we are looking at the legacy of these giants. We cannot see them anymore. They have all burned out long ago, lost to the dark ages of the cosmos. No telescope, no matter how powerful, will likely ever capture an image of one in detail. They are ghosts. But their ashes are in the ancient stars of globular clusters, and their ghosts are the gravity that holds our galaxies together. It is a humbling thought. The universe we live in today, this calm, orderly place of stable stars and planets, was built on the shoulders of monsters. We are essentially stellar archaeologists, sifting through the chemical wreckage of a violent, beautiful past to understand how we got here. It seems that in the early universe, there was no limit to the grandeur of the stars. And thanks to instruments like James Webb, and the future extremely large telescope, ELT, currently being built in Chile, we are finally meeting them face to face. Thank you for watching. If you want to dive deeper into the mysteries of black holes and how they shape the cosmos, check out this video on the screen right now. Until next time, keep looking up.